Tutorial 1, Part 3, Elemental Stability and Primary Bonding. For definition of chemical terms such as metals, semi-metals, and nonmetals, please refer to the lecture. Atoms tend to have their valence shell filled fully by electrons. For sp Bohr elements, that is, elements with fully filled outermost shells will be most stable, such as those noble gases. And therefore, noble gases will rarely form chemical bonds with other elements. For other elements, they will try to form chemical bonds, which is primary bonds, to attain such valence shell fully filled structures. And there is 3 types of such bondings: metallic, covalent, and ionic. They are all coulombic in nature, which is the electrostatic attraction. There is a attraction force between electrons and nucleus, but there is also a repulsion for R small enough, which is due to the Pauli exclusion principle, which again quantum mechanics. And the energy, the bonding energy, is basically the area under the force and separation curve. And you can see it here in the picture here. You can see that in a large separation, the force is small, and it slowly goes to a maximum value for a smaller R, and it suddenly has start to decrease, and finally it can become repulsive due to the Pauli exclusion principle. At this region, it is mainly due to the Coulombic attraction between the opposite charged particles. If you try to integrate it, you can find that the energy profiles. Metallic bond, which only exists between metallic elements, which is mainly in group 1, 2, and some d-Bohr transition metal, and some elements in group 14 to 17 in pre-Bohr, which is result from the attractions between the valence electron C and possible positive metal ions. As the electron numbers in the valence shell is very few, when the atoms try to give off this valence electron, their inner shell is already fully filled. Just by giving out these extra electrons, they can achieve the valence shell structure. And therefore, for a large quantity of these metal atoms, they will form valence electron C. The electron is come from those valence shell electrons and are positive metal ions. And for main group metals and transition metal, they will drop electrons in the s orbitals, in the outermost s orbitals first. For example, Na is in group 1, and that means they have 1 electrons in their valence shell, and therefore Na will form Na plus, which is ion. And calcium is in group 2, and they will form calcium 2 plus by giving up the 2 electrons in their valence shell. Bonding nature, because this is quite a number of electrons and quite a number of metal ions, the attractive force is everywhere and it is non-directional, and usually the bond strength is lower. And in a higher period down the same group, the metallic bond, the trend of forming the metallic bond is easier, because as the distance between the outermost shell electron, which is usually the valence shell electrons, becomes larger between the electrons and the centered positively charged nucleus, and the Coulombic attractive force become smaller, because therefore they are easier to develop their electrons. Of such primary bonding, you can see that the metal atoms give up their outermost electrons to form metal ions, and those free electrons form a sea of electrons. Here is an example. Find Fe3 ion, which is Fe3 plus electron configurations. First, we find the original Fe first, which is the ion atom electron configuration, which is in this way. You can use different methods, as I mentioned in the earlier PowerPoints. Transition metal will also drop S, the outermost S orbitals, the electrons in these orbitals first, and therefore, because 3 plus, that means 3 electrons is missing. For S2, there is only 2 electrons is already give up, and 3d6, there is still 1 need to give up, and becomes 3d5. And therefore, it have the following configurations. Is a bonding results from the electrostatic attraction between close packed and opposite charged ions. It is generally formed between metals and nonmetals. Metals tend to give away their excess electrons and form positive ion, and nonmetals tend to form negative ions to fill up their valence shell. Because for nonmetals, their valence shell is almost filled up, and they just require some extra electrons to attain the stable structures. For example, stable ions for oxygen. Oxygen have electron configurations of this way. Is O2 minus. 2p4 is not completely filled up, and 2p6 is completely filled up. And there is 2 more excess electrons in this way. The bonding nature for this bonding, ionic bond, it is also non-directional, and the bond strength is directly proportional to ion charge, but inversely proportional to bond length, which is again due to the Coulombic attraction. Bonds have a such structure for the materials, and you can see negative ion, positive ion, negative ion, they are arranged in a regular way. And this is non-directional because this is everywhere. The ions exist in magnesium phosphate, which is a compound consists of only magnesium and phosphorus. First thing, what is the likely bondings between Mg and P? It is obviously ionic because magnesium is a metal, phosphate is a non-metal. Step 2, we obtain the valence shell electrons from the periodic table. Mg, it is in period 3, and it is in S block, and it is in group 2, therefore it is 3s2. It is the valence shell, and the valence shell electron number is 2. For P, the outermost shell will be 3s2 and 3p3, and that means it have a total valence electron number of 5. And then we determine the ions form. Ng will give away 3s2 to form Ng2+, which in the rest, and the Ng2+ will have a electron configuration of 1s2, 2s2, and 2p6, which is same as neon. P, phosphorus, will accept 3 more electrons to form P3-, which have a configuration of 1s2, 2s2, 2p6, 3s2, and 3p6, which is same as argon's electron configurations. And that's how we predict the ions exist in such compounds. Bond. Covalent bond is a sharing of electron pairs between atoms to form molecules, which generally exists between nonmetals. Bonding nature, it is directional, and there may be hybridization of electron orbitals, which is a combination of different subcells in order to achieve a stable structure and geometries, and the bonding energies is usually higher. Here is an example of hybridization in the H2O molecules. H and O will form covalent bond between each other. And for hydrogen, they have only one electron in their valence shell, and they will share one electron, the only one electron to oxygen. And oxygen in give back, they will also share one electron to hydrogen. And hydrogen, therefore, in their valence shell, they will have 2 by this way. And for oxygen, because it is bound to 2 hydrogen atoms by this way, it will have in total 8 valence shell electrons, which is fully filled for oxygen. You may want to ask why hydrogen and oxygen atoms will form H2O. The reason, as I just mentioned, is due to by sharing of those outermost shell electrons, they can both form stable, chemically stable species. And by this way, they form molecules.